Hi, this video is going to be covering special right triangles, which you would have first learned in geometry and then again in Algebra 2. And these are the triangles where they are special because their trig ratios and their angles are all rational numbers. Okay, so what I mean by that is typically if we have like a, say we have a triangle where we've got, your basic 3, 4, 5 triangle. That's a Pythagorean triple, one of the ones where all the sides happen to be exact. So sometimes it's possible to draw a triangle that is all exact sides like that, but this angle is not going to be a rational number, and neither is this. So most of the time when we have a right triangle, we might have sides that are exact, but we have an angle that's not something exact. You're going to get some kind of a decimal answer. Or we might have an angle that's exact, like let's say we get a 35-degree angle here, and then if we we know this is 15 and we try to solve for x, we're going to get a irrational number there. So these special right triangles are ones where the relationship between the angles and the sides is a rational relationship and something that we can memorize as a formula rather than using our trig ratios. So I'm going to start with the 30, 60, 90. I always like to show why the formulas are what they are in case you happen to forget them. So there are formulas for special right triangles and relating the sides, and there is a formula for 45, 45, 90, and they're pretty simple for where they come from. So because I've drawn a 30, 60, 90 triangle here, so that side is labeled as 60, which would mean this one would have to be 30. Obviously we have the 90 indicated here. So the way that we can kind of derive these formulas is what I'm going to do is I'm going to extend the side. I'm basically going to like mirror this image. So I'm going to draw another 30, 60, 90 as best I can over here on the other side. So imagine I've just reflected this triangle around its long side. And what happens if I do that is now there's some things that I know. So I know that, okay, I'm going to go ahead and call this side x. So I'm referring to the short leg here. So now what I know is, okay, what kind of a triangle have I formed, like the big triangle? So this triangle has a side of 60, an angle of 60, 60, and a 60, which means this triangle is now, if I reflect this small triangle across itself, any 30, 60, 90 across itself, we make an equilateral triangle, which means we know all of these sides are the same. Which means I could label, if that side there, that short leg that I've labeled as x is x, then I know that this must be 2x. Because that is half of this side, which I know is the same as this side. So that's our first formula basically for a 30, 60, 90 is the short leg times 2, or 2 times the short leg, equals the hypotenuse of a 30, 60, 90 triangle. Okay, because that's half of that equilateral side of that equilateral triangle. So then what about this longer leg? So we call these the legs, by the way. Short leg, long leg, hypotenuse. So the long leg, once we have kind of 2 of the sides, we know that this is always double. That's the easiest one to remember. Hypotenuse equals 2 times the short leg. Now this is the long leg. So if I labeled this, let's just call it B for now. This is where the long leg comes from. So if I have 3 sides, then I can use Pythagorean theorem to find that third side. So I could say x squared plus b squared has to equal 2x squared. I'll do a little simplifying here. So 2x squared is the same as 4x squared. I got to square the 2 as well. And then I could subtract x from both sides, or x squared. And then to solve for b, I would take the square root of both sides. So the square root of x is x, or of x squared is x, and the square root of 3 I just have to write as the square root of 3. So b is the square root of 3 times x, or what we can say is square root of 3 times the short leg equals the long leg. So those are our formulas for 30, 60, 90. If you want to kind of, streamline this, we could say 2 times the short leg equals hypotenuse. Actually, I'm going to try, I think it maybe usually would write it like that. Hypotenuse equals 2 times the short leg. Long leg equals short leg times radical 3. And those are our two formulas for 30, 60, 90. So why do we use these formulas, or how do we use them? Is we use them so that we don't have to bother with trig ratios. So for instance, if I know that a triangle is a 30, 60, 90, so that would just be indicated by them giving me one side, or one angle, and I knew that the long leg is 12. Okay, now I said long leg is 12. I probably should have just said one of the sides is 12, and let's talk about how I know that's the long leg. So, I mean, I have a leg that's opposite of, I know this angle is 30. I know that this side is obviously longer than this side because A, it looks longer, but B, it's across from the larger angle. So this would be my long leg. So 12 is my long leg. And I need to find my short leg. Let's say this is X and let's say this is Y, and my hypotenuse. So my long leg here is 12, so I would refer to my relationship that I know. So I know that long leg equals short leg times radical 3. So in this case, that's X. So I'm just using this formula, plugging in what I know, which is the length of my long leg. And then I could just divide by rad 3 to get my short leg. So you always want to go to the short leg. That's the one that both formulas have in common. So I've got 12 over rad 3 is X, and I'm just going to rationalize that. Multiply by rad 3 over rad 3. 12 rad 3 over 3, and then I can simplify to 4 rad 3. Now I know my short leg is 4 rad 3. And then if I want my hypotenuse, I'm not going to bother with doing sine of 30 over whatever. I'm just going to double my short leg. So my hypotenuse is 2 times the short leg, so this would be 8 rad 3. So using your formulas, it's all about being able to find those values exactly so that I'm keeping this exact, able to write it as a rational number. Well, it's not rational, but I'm keeping it in exact form. Rather than having it be an irrational decimal. And it's the only, these are the only triangles where we're able to do that. Okay, so that's your 30, 60, 90. I started with the harder one because it's got the 3 parts, which means we have 2 formulas. And then on to the 45, 45, 90. So this one's simpler because the thing we know about a 45, 45, 90 is if it's 45, 45, it would be an isosceles triangle. So that angle and that angle are the same, both 45, and that would mean that that side and this side are the same. So we've got 2 sides that are X. So we only need one formula about the hypotenuse. But we can use the same strategy that I used for the 30, 60, 90, which is that I can use Pythagorean theorem, where I want to find my hypotenuse. So let's call it H. So I could say that x squared plus x squared equals h squared. 2x squared equals h squared. H equals the square root of 2x squared. And the x could come out of that, so x times the square root of 2, or the square root of 2 times x. And so that's my formula for the hypotenuse of a 45, 45, 90. Hypotenuse equals short leg times radical 2, or leg. There's no short leg, it's just leg because they're the same. Now, you can memorize these formulas, or you can think of it more as image-based formulas. So I'm going to just kind of replace this image. So if those are x's, then this is x rad 2. And I'm going to go and replace the previous image as well. So up here, just kind of completing this image, I'm going to take away that addition to that drawing. So if I've got x, the hypotenuse is 2x, and the long leg is x rad 3. So this is essentially your rule for 30, 60, 90, and this is your rule for a 45, 45, 90. Same thing, if we want to solve and we have a 45-degree angle, that could be indicated to us by just the symbol that our angles are congruent. And maybe I give you the hypotenuse is 12. I guess I'm just using 12 all the time. And we want to find x, then we would say that I know that 12 is equal to x rad 2. And then I divide. 12 divided by rad 2. Rationalize that. Six rad 2. Okay, and those are your special right triangles, 45, 45, 90, and 30, 60, 90.